Okay, everyone, welcome back to the second part of the Week 12 lecture. This is I guess, a little quick, easy and interesting way to end the session. And in some ways it's sort of violating a lot of the principles that we've talked about throughout the semester, but there is a practical thing to think about, which is getting your career started. You know, exciting young people, getting your foot in the door in a school and being seen as someone worth investing in and perhaps worth having their own class, becoming a full-time member of staff. So I've compiled together here some quick hitters, some scientific investigations that are fun, that have good educational value in isolation, and have materials that you can carry around in the boot of your car fairly easily. I know that I have used in my previous life as a teacher quite a number of these activities to set myself apart as a casual and to add something of value to the school. And more often than not, those did result in more casual days, more weeks of relief teaching, and those sorts of things as well. So have a look, but do remember these are not designed to be fully developed 5Es type of work. It's more things that you can do in a quick 40-minute block at the end of the day to have a positive impact and build rapport and create excitement. So we won't go through this, but it's important to think about how these relate to working scientifically in design and production as you go through. You can probably gather that from the verbs, but I won't go through those right now. So why do them? Look, you can't always design and deliver high quality science units until a school gives you that opportunity and puts you in a position to do that through a long-term contract. So if you're doing casual work and you're doing day-by-day work, you can't really go through a full cycle of 5Es and develop things in that sense. So we'll have to put those things aside and ask us, how do we get that opportunity? Well, sometimes it's important to put some wow factor into our teaching, get some excitement, advertise ourselves so that we can do the deep, rich science learning that has underpinned EMS207. So a couple of tips. Be sure to develop your teaching resource kit now. You'll usually need it at a moment's notice. I had sort of an old plastic box container with various sort of liquids and things, running around in there as well. Tennis balls, basketballs, all sorts of crazy stuff. Many of the activities need to be presented in a teacher-centered way, so they kind of go against what we've talked about because you won't have the resources to do it with all the youngsters around the joint. But it can open up the door for future investigation. You can use that to leverage more resources if it proves helpful. So doing some quick science in your afternoon session can get you recognised as a hard-working casual. And I've managed to get 2-week blocks out of it. So the investment pays itself off quite quickly. So the investment in quick-hitting science can actually, it'll more than pay itself off if you get a single teaching day out of it. So a couple of ones that I like, and these aren't the be-all and end-all, the internet's your friend here, as most things are, but one thing that I quite like to play around with is this idea of water density. And the molecules of water, the H2O water molecules, change their behaviour and interact differently depending on the temperature of the water. What this means is that if water is hot, it will not readily mix with cold water, because the molecules are moving quite violently and they're taking up more space. And this is why we have currents in the ocean of hot and cold water essentially bypassing each other. Although that doesn't make sense to children in many respects. So we can show them this through a demonstration. The demonstration itself is a little bit dangerous. I guess you've got to have some hot water. So you'll have to do this very much in a teacher-centered way, perhaps in a wet area. But what you will need are clear containers and food dyes. That's it. And maybe somewhere to heat up some water. So the key variables here, we have a water temperature and salinity. So you could play around with adding salt to the water or having water at different temperatures and seeing what impacts this have on the interaction of the water of different temperatures. But it's a great one-off to actually engage the students. There's something artistic about it. And I'll give you a little example. So here on this YouTube screen, we have the little example of this. And I'm just going to pause it there for a second. Basically, what's going on here is red dye is being poured into the hot water and it's divided in the middle. I've used fish tanks for this sort of stuff as well with little dividers in the middle. And you have the cold water in the other side. This person's got red dye for, because we need to see the movement. So we have different dyes to show us the different temperature waters so we can see how they interact in a way we couldn't if we didn't have the food dye. So food dye is great for many reasons, and this is just one of them. So you can see here when they play this, I'm going to turn the sound off on this one so I can talk, but what we end up with is the different pathways and the currents happening with the hot water originally moving over the top of the cold before eventually the temperatures, it intersperses and the temperatures become more uniform. So it's a really interesting one. We'll look at another one here as well. Same thing, red is hot. Oh, anyway, I don't want to continue playing this. So we'll continue through and have another look here as well. Another one that I like, you can watch this, is tornado jars. It's a really simple, more an art piece than anything else. But students really like this. And essentially what you need are a glass jar, detergent, and other liquids and food dyes, because you can experiment with different liquids. And essentially what it's acknowledging is the different sort of surface tensions and different viscosities of liquids prevents them from mixing directly, even though they seem to be liquids. So what you do is essentially put in a jar, fill it with water, put in some food dye and some glitter if you want, but you put something in like food detergent or oil or something, so that you can actually get a separation and create allow centrifugal force to occur to create a tornado or a vortex. So students will likely find this extremely engaging. They'll want to experiment with different liquids and materials in creating them. And you'll need someone to do a bit of shaking. It's pretty safe. You can get kids to do this. In fact, I'll probably come into school with their own tornadoes in a bottle afterwards. But I'll just give you a quick sense of what they look like. This one has, hang on, turn this one off. Get through the ads, sorry, the ads are obnoxious. I'll turn that off. So you can see when you shake it, we don't get the full, we don't get the complete combination of the liquids. They stay separately. So the detergents have nothing to attach to, so they stay together. There's nothing to kind of dilute. And they'll create a really nice ongoing vortex because it won't fully combine, and then it will return back again. So it's definitely a bit of fun. I think oil works really well with this, but the choice is entirely yours. So I'll get rid of those two. The next one I would like to talk about is, we'll skip through that, is a nice one, modelling the phases of the moon. You've heard me talk about this quite a bit throughout the semester. So I'd like to show you what this looks like. Essentially, the way you can model the phases of the moon is through a lamp, a tennis ball, and any other ball that the students might use. So we need a source of light to represent the sun, and usually a tennis ball to represent the moon. And we often can use ourselves in a swivel chair to represent the earth. So this will show students the different phases of the moon, and we can use this in an open way, where you go, here are the materials, here's the lamp, here's the tennis ball, here's a basketball, whatever you like, show me the phases of the moon. So it's a really wonderful open investigation. And if necessary, you can use it as a content representation to show how the phases of the moon actually change. I mean, I've done this in a K-6 setting, and I came up with all sorts of bizarre explanations as students tried to create the phases of the moon. But we'll have a look at a quick example here, which I'll bring in from off screen. So you can see here that you have the person turning. So we've got the source of light, perhaps the tennis ball there, and they are turning around, acting as the Earth's rotation, in a sense, the Earth's orbit. Yep, that's the thing, and we can see the movement. From our perspective, notice how the moon always is lit up in the same way. That's where we get the term the dark side of the moon, because it's always the same side of the moon being lit up and not. But the perspective is what causes the phases. So we see here from sort of the GoPro cam how this actually works from our perspective on Earth. So you could have the students record something similar. We have essentially no moon there, or a new moon. And then it continues through, and then suddenly we have the waxing crescent or crescent moon. And then as we skip through, we have the first quarter moon, and then it makes the correct shapes, the correct curvature, unlike an ellipse. So it's a really simple investigation, but it does lead to those sort of wow moments when you show students. Excuse me. The next one here that I'd like to speak to is Foucault's pendulum. So this was actually the first simple proof that the Earth's that the Earth actually spins on its own axis, that the Earth actually moves. Because if you tell young people the Earth is moving, rotating on its own axis, they won't believe you because it doesn't feel like it's moving. You know, if I stand still, I feel like I'm still. And so we're moving at about 900 kilometres an hour, which sounds ridiculous, but that's the truth of it. And students often rightly, from their own observation, incorrectly think, that the sun is moving around us, a geocentric view of the world instead of a heliocentric view. So how do we prove this to them? How do we not just say, trust me? Well, the first time this was ever proved was through, was he Austrian? Through a fellow called Foucault, who realised that if you rotated a pendulum on its own axis, it would eventually move off that axis because it was separate and independent from the Earth. So if you watch something like this, you could do time lapses of these as well. You'll note that this pendulum was originally started along that line there, and as time's passed, it's moved along. And eventually, with no interruption, no pushing, no anything, it will hit that particular, a water bottle. And so you will eventually see, with no intervention at all, the striking and the changing of the angle that it's actually rotating at. And we can see that happening automatically. This will happen everywhere on Earth. If you start a pendulum and there are no other forces clearly acting upon it like wind or friction or something, it will eventually change completely and rotate as the Earth spins. So we have this proof. Now this is great if you're in a museum, but of course most of us aren't in a museum. So you can actually do this yourself in a classroom setting. So the way you could go about this is attach a bucket of sand to the roof with fishing hooks or wire or rope or whatever you like. Something nice and heavy that you can have move. So you hold it and tie it until it is as still as possible before releasing it in a pendulum fashion. You can do this with, holding it together with kind of clamps and things like that, and then like cutting the twine and things like this. So you can keep retweaking this to prove students correct or incorrect. So some will often say, I'll only move because there was wind in the door. So you can shut the door, turn off the air conditioner, have everyone remain still, give bandanas to reduce the effect of breathing. So you can control all those variables that you think might be having a force impact on the pendulum. But you can control all of them, but it will continuously rotate off its axis because the Earth is moving. It can be done in a good 40-minute lesson. And what this means is students have nothing, they cannot disprove it, and they are left solely to understand that the Earth must be moving underneath them. Has to be, because of the change in the pendulum swing. So that's a pretty cool one. We can do content states of matter representation. So content representations for the states of matter, like what is happening to the water molecules in an ice cube to liquid to gas, for example. And we can have students actually perform this themselves. So very simple, very basic, no material needed other than your class. And here's a fellow doing one now. I might just turn the sound off on that. I'll leave the ad out of the recording for you. That's what I'll do. Okay, ad's gone now. So you can see here we have the teacher, and he has the students currently acting as an ice cube. And so each of them represent a molecule, obviously a pretty flawed content representation because of the size alone. But the students act together, and he will eventually sort of suggest heat is going to be applied. So let's move this up. So now heat's being applied, and he's showing the movement of the molecules. So the kids have to sort of stand there and move to show that the heat's happening. As heat continues, the movement gets more and more wild, and eventually what will happen is they break apart and become gas. So all the molecules are now completely separated, and we have gas, and then they come back together in a less connected way with lots of movement and become water. Very simple, but a wonderful way to show conceptually what is happening at a molecular level when you're getting state changes in states of matter. So really, really helpful, and it does apply directly to our syllabus as well. One of my more interesting questions, and this was posed to stump me in one of my favourite K-6 schools, a student asked me, well, why is the sky blue, Mr. Dean? And truthfully, I didn't really know. Had no idea. And he suggested it was because the ocean's blue, and it's the lights, the ocean's being reflected back into the sky. And that was quite interesting logic. I suspected he was wrong, but I went and looked it up myself. And what I realised was it's something called Rayleigh scattering. So the properties, the chemicals in our atmosphere, the gases in our atmosphere treat blue light a bit differently to everything else. And what they do is reflect it, and it bounces off continuously before it even gets to the Earth. And in fact, if you look very closely at a horizon, you will notice the colour of light, the blue in the sky, actually dissipates the closer we get to the Earth's surface. It gets to be that little white strip, that slightly grey-white strip towards the actual horizon where the Earth, the ground appears to meet the sky in our eyes. That's what's happening. The blue light is effectively being filtered out at some level. And we can actually see this when by using a very simple activity using small mirrors, blank sheets of paper and containers, water containers. So knowing that white light is made up of all of the colours of the rainbow together, but we can actually, what we can do is half fill a container with water, go outside on a sunny day, put our mirrors into the water so that we're getting a refraction, so we're refracting the light and separating the colours, and then rotate while the mirror is half submerged, rotate and angle the sun's light from shining off the mirror towards a piece of paper. The piece of paper will show all these wonderful colours. The refraction will show us all the colours of the rainbow except one, blue. Blue won't appear because it's been previously scattered. And it was really fascinating because I had young people coming through, trying to say they found little bits of blue. Obviously, it wasn't entirely correct, but it was paled in comparison to the purples and the yellows and those sorts of things. Really fascinating stuff. Great for artistic expression as well, and it worked for me for a nice little group work activity. Very simple because it was quite light on materials. So I did that in a K-6 setting. If you do want to see the investigation behind it, you can actually see that there. Notice the classic whiter horizon for that reason. And you can sort of see some of the science behind it with the blue light being scattered from the Rayleigh scattering effect. And yeah, if you want to get into the deeper science behind it, like the specific gases that cause that effect, you can, but we won't do that for a quick hitter, I don't think. It doesn't seem entirely necessary. Another one that I like is the floating paper clips activity. You can look at the background on this if you wish to do so. But basically, there is an acknowledgement that when you have water molecules in water together, they tend to bind together at the surface as they're facing a different temperature. I guess it's a really mild version of what we see in a formal state of change. And so there's this slight binding together that creates the meniscus, the surface tension of water. It's the reason why things like leaves and very light material tend to float on water. Because of that meniscus, it provides a really slight bit of tension that can actually hold up very light things. So there is an investigation that can tap into that, and more of a challenge, where you can ask students to complete the paperclip challenge. Basically, tell them you can give them, something. The challenge is, can you get a paperclip to float on water? As a general rule, they will not believe that it is possible to achieve that without some sort of intervention. So what you'll need are paper towels, paper clips, small containers, and other liquids to introduce if you want to play around with variables, like detergent. What you'll rapidly find is detergent tends to weaken the surface tension of water, ending your floating paper clip, so to speak. So what I do is use a discovery approach with this. I ask the students to try and make a paper clip float in the water unassisted. No paper, no flotation devices, nothing. And they'll struggle and try and struggle and think, most importantly. But if you want to know the true answer to it, the trick is to actually place the paperclip onto the paper towels and allow the paper to sink ever so gradually, because the paper towel will absorb the water, become too heavy and fall down. But it's such a slow process that the paperclip will be placed so gently that it actually won't break the surface tension and will continue to float. It is a fascinating thing to observe, bizarrely satisfying as well. So at the surface, basically water molecules are more intensely attracted to each other, which creates that very slight sense of surface tension that means something like a paperclip can in fact fall on it, float on it. So I'd recommend giving it a go. It's really cool. You can do the same thing if you want to do it with balloons. If you rub a balloon on wool to get static electricity and create a nice little zap, the classic thing we've all experienced probably as kids when we're going up and down a slide, you can charge a balloon by rubbing it on wool to get excess electrons, and then move that next to a very light flow of water on a tap, and it will appear to push that. And the reason it appears to be pushing is the electrons are actually trying to jump into the water because it's a conductor. So that creates slight force, and you can actually appear to bend water without touching it. Kids love it because it makes you look like some sort of magician. You can do lava lamps as well. They're pretty cool, I must say. They're more giving us a sense of chemical reaction in a way, and giving us a sense of the different surface tensions of liquid. So it's not hugely aligned to what we do in the primary science syllabus, but it is pretty cool. So if you want to check it out, you can see, a bit of a, you just need those fizzing tablets. Barocca tablets are where I go for this, but you need something that will fizz basically and send up a bit of carbon dioxide into the atmosphere. If you want to see what they look like in practice, the way to do them is put a lot of oil, just olive oil will do the job, and water, which will not mix in any circumstance.
And let's put about 8 drops in.
So we can see this fellow here. Then you put in some food dye. And notice it very slowly goes through the oil because of the different viscosity of the liquid. It doesn't quite mix, and the bubbles stay intact, which is really visually appealing, I must say. And those are the parts of the that we'll use for the lava lamp. Then you put in your Barocca or any fizzing tablet, basically, as this chap's about to do. You drop that through. Obviously, it's so heavy it goes through the oil and the water. That's the important thing here. It's not a liquid, it's a solid, so it travels through both and then begins to have its chemical reaction. It's now fizzing. And that carbon dioxide that has been produced has to go somewhere in the reaction. That air has to go somewhere in the interaction. So it goes back to the top. So we get that lovely bubbling effect. But what it does start to do is pull out the red food dye and send them up there in a very visually appealing way. And you can just do that repeatedly. And it's a waste of particularly good pills, potentially, Barocca. But the kids absolutely love it. It's a great little activity to do at the end of the day, and I've had a lot of joy teaching students about that. Nice, simple one there. The next one are building bridges. I like this as a really easy to use project or problem-based learning scenario. That's generally how I feel about it. So the way we do with this one is we generally get a bit of a kit of things like paddle pop sticks, which are quite cost effective at little $1 shops. Paddle pop sticks, sticky tape, rulers, straws, scales and weights. We need scales and weights of some sort, and they're usually available in most classrooms and schools, is so that we can test our bridges. So what you generally want to do with this particular activity is create a design brief for the students. They have to use core materials. They will all have the same number of materials, so you keep things fair and consistent across groups. It's a great group learning tool. And tell them they need to design a bridge where it covers at least 20 centimetres, so perhaps between two tables, and holds at least 500 grams of weight consistently. So it creates a nice challenge environment, and it brings in clear links to mathematics. And you allow them to plan and design those bridges in ways that you feel are appropriate. You can structure that heavily, you can leave it entirely open-ended, you could do roll cards, all sorts of great opportunities. Then what you want to do, the fun part, is testing the bridges at the end by adding weight incrementally. So we discuss things like fairness. Should I drop my weight from a great height and cause more power to disrupt it, or should I place it gently? We record and graph the results, discuss the findings. So there's some really great opportunities to expand this out, think about the quality of our question, what the bridge is designed for, is aesthetics a part of it? So you can link that into society. We can look at examples of bridges. We can do some cultural connections to things like the Sydney Harbour Bridge. You name it. It is a very simple activity that fleshes out really nicely. This building element will pretty much win every student over, and it's a little bit more resource hungry, and you need some stuff for each student. You can do variations of this, like building towers with marshmallows and uncooked pasta. Like, you can simplify this in a way and do different challenges. But this idea of a challenge component, like even something like building parachutes with like freezer bags for army men, can do this as well, because they can play around with designs, drop things, weigh things, all sorts of great stuff. There are lots of STEM learning activities out there as well that should probably be considered. So there's the bridge building stuff there, if you want to have a look at it. It's pretty simple. My explanation is probably good enough, to be honest. It's not a particularly complex activity. And the Department of Education does in fact provide some examples of STEM activities. So you can see designing an environment for a wombat visit, future vehicles in stage 3, invent an outside game, knock over a block tower is pretty fun. These are all nice and easy and aligned to the syllabus, so you could obviously pick a stage level and go, I want to look at native animals and do some STEM work with that. And it generally provides you with documentation and workbooks as well that you can use in your teaching. So you are supported and guided towards that through the Department of Education as well. So we're not out of sync or step with what they're talking about. So there are other important resources to factor into the mix here as well. There is, of course, your own research, the internet books, etc. Your colleagues in particular are an important asset, and subject coordinators and tutors are a really big aspect to all of this. People like myself and the people who've worked with you will give you great bits of advice and things like that. I'd recommend creating a thumb drive. I mean, that's a bit old school, or a share drive with Google Drive where you can hoard these bits and pieces and use them when you see fit, because we need that big base not only of teaching strategies, content knowledge, but materials and resources to enact them. Remember, just to finish up here, these are of course just quick hitters. They cannot replace the deep learning, the focus on language, the time to communicate, the conceptual work that is done through EMS207 that represents the ideal. But we would rather an enthusiastic and capable science teacher like yourself use the tricks of the trade to get into a school and have a good impact. So these are certainly important elements, but curriculum content and scientific literacy should remain the key goals here through your questioning and how you frame this stuff. Anyway, this is the last lecture, so thank you for watching. I mean, I'll probably be able to tell on YouTube how many did, so we'll see. Complete any tasks set by your lecturer coordinator. Check out IWBs if you want to. I don't think it's too relevant. Bring a draft of your report with the alternative conceptions work to this week's tutorial, because we really want to flesh that out and make sure you're in a good position for the final assessment task. Bring the latest version of your digital learning resource for more feedback if you would like as well. And of course, a reminder, the assessment is due on Friday the 24th of May. So if you've listened to my lectures, thank you very much. I've enjoyed being able to contribute to the subject, even in a small way. And I wish you all the best of luck in your future teaching careers. And we hope to hear from you moving forward as well.